Hello, everyone. Thank you for joining us today. Welcome to the Innovation Leadership at Synopsys session, where we'll be talking about solutions for optimized chip design, implementation, and verification that have been jointly developed by Synopsys and ARM. My name is Neel Desai, and with me I have Holger Keding. We will be jointly delivering this presentation today. Holger is a senior staff engineer in the verification team, and I'm a part of the ARM Solutions Group, a recently created centralized organization to help accelerate the development of flows and methodologies that in turn will help you accelerate the development of ARM processor cores. If you have any questions, please use the chat function to submit these, and one of us from Synopsys will respond back to you. If we can't get to all the questions today, we'll get back to you as soon as we can after this session. Also, at the end of the presentation, we'll leave you with a whole bunch of a slide with QR codes. We're going to be talking about a lot of technology today. And if you scan those QR codes, you'll be taken to a landing page where you can get more information on the technologies that we'll be covering today. So ARM and Synopsys have been collaborating extensively for decades to enable solutions for our mutual customers across the entire chip development flow. This includes optimized implementation, which is digital and custom, hardware design and verification, system validation, software development, and hardware-software integration with emulation, virtual hybrid and FPGA prototyping, and of course, software security. So very critical for today's designs. So essentially, we have you covered for all aspects of your design success requirements. Unfortunately, today, we only have time to cover really two areas because we only have about 30 minutes. So we'll be talking about optimized implementation that you can see on the top left there, and virtual prototypes that you can see on the bottom right. If you would like more information on the other areas that we are not able to cover today, I encourage you to go to synopsys.com/ARM. So I'm going to be covering the optimized implementation section. We will take a look at reference implementation flows that can get you to the best PPA for your ARM CPUs. And I'll also touch upon many of the recently released advanced technologies that you can use on your designs today. So first, let me introduce you to Fusion Design Platform that includes Fusion Compiler. I'm sure many of you are already using this platform today for your design tapeouts. Fusion Design Platform delivers full flow quality of results and time to results to accelerate the next wave of innovation that all of you are driving with your designs. It is the industry's first AI-enhanced and cloud-ready platform that leverages machine learning to speed up analysis and optimization, resulting in significantly improved PPA. At the heart of this platform is Fusion technology that essentially redefines conventional EDA tool boundaries across synthesis, ECO, place and route, sign-off by sharing integrated engines across the complete digital design product line. And talking about cloud ready, for those of you that are using cloud solutions today, this platform is available on Microsoft Azure, Amazon Web Services, AWS, Google Cloud, and Synopsys Cloud Solutions. Fusion Design Platform enables designers to accelerate the delivery of your next generation designs with the industry's best QOR and TTR, quality of results and time to results. So I'm sure you're all wondering how you can quickly and easily leverage all the goodness of Fusion Design Platform for your ARM core-based designs today. This is where the decades-long collaboration between ARM and Synopsys comes into play, and it's so very important. ARM and Synopsys start working on core-specific reference flows very early in the ARM core development cycle, as early as alpha and sometimes even before that. This early collaboration allows us to develop new tool capabilities and methodologies while the core is still in development. So when the core is finally released, starting with early adopters of the core, we have a solution that includes recipes and methodologies to achieve the best PPA on these cores. We call these reference flows Quick Start Implementation Kits, or QUIC. The latest QUIC for Cortex A78 and Cortex X1 was released pretty much at the same time, actually at the same time as when ARM announced these cores. So let me tell you a little bit more about these QUICs. Quicks are the best start point for ARM CPU implementation. Quicks include a full RTL to GDS2 implementation, test, ECO, sign-off, and formal verification flow. They are fully worked examples, meaning that we have achieved a specific, aggressive QOR target as set by ARM. They are architected for you to be able to easily adapt to your course specific needs. One size doesn't fit all. You have to adapt these quicks for your specific core configuration, flow plan, technology node, design style, and whether it's hierarchical or flat, and design goals. The bottom line is that quicks help you get the best PPA for your advanced ARM CPUs using Synopsys Fusion platform. And the benefits of these quicks and the resulting benefits of the collaboration, I should say, and the resulting quicks are evident in the growing number of customer tapeouts of ARM processors using Synopsys. Many of the successes are public. For instance, what I'm showing you here is an excerpt from a recent news release in support of ARM announcing the Cortex-A78, X1, and the Mali G78 cores, where Synopsys announced successful tapeouts of these cores at large leading-edge customers that leverage the quick for their SoCs. The success of this customer and many such customers can be attributed to the almost 3-decade-long partnership that we have at ARM, a close engineering-level partnership that continues to grow stronger. Today we are working together with ARM on so many multiple cores, on multiple technology nodes, targeting a range of markets than ever before. And really, the heart of this collaboration that is enabling these customer tapeouts is Fusion Design Compiler. I should say Fusion Compiler. Fusion Compiler is the industry's only full-flow RTL to GDS2 product. And it has 3 key benefits over any other solution available today. It is built on a single, highly scalable data model that essentially brings together the entire flow from synthesis all the way to sign-off. This single data model allows designers to leverage common engines throughout the design implementation and interleave them as needed for best PPA. It leverages Synopsys golden sign-off technologies to minimize design margins and thus maximize overall PPA gains. What is key here is that Fusion Compiler consistently delivers the fastest and most predictable flow results, achieving the best PPA, or like what we like to call it, simply better PPA. So you can see on the right-hand side, a couple of results that I want to share with you. These are just 2 of many successes that we have at Fusion Compiler on ARM cores. And I'm sharing with you 2 examples on X1 and Neoverse. X1 core is in 5 nanometer. And you can see the PPA predictability is evident throughout the progression of the design flow. You can iterate, customers or engineers can iterate in the early architectural phase of the design flow, knowing that the design will close and hit the high performance goals at the end. The second example is a customer benchmark on a data center focused Neoverse N1 ARM core, which is in 7 nanometers. Fusion Compiler beat the competition on both PPA and time to results. And it's important to note that this was using the out-of-the-box quicks. And it was set up and running in a matter of days to get the results compared to what took the competition weeks to achieve. Okay, so I'm sure you're wondering how you can get access to these quicks, your fast track to achieving the best ARM core PPA goals. And this is really the simple part. You can request quicks from Synopsys SolveNet, or for some of the newer cores, you can actually get them directly from ARM. So it's very easy for you to get access to these quicks and start designing your ARM core based projects. Okay, so I've talked about the deep and broad collaboration between ARM and Synopsys and quicks for getting the best PPA for ARM cores, but what about the rest of the design? So in the time that I have left, I will give you a brief overview of 4 of the latest innovations from Synopsys to help you get the best PPA for your complete design. Let me start with machine learning. I briefly spoke about this when I introduced Fusion Design Platform. Machine learning is deployed across the Fusion Design platform, and it enables better QR and faster TTR by speeding up the computation-intensive analysis, predicting outcomes to improve decision-making, and leverage past learnings. Then there's RTL Architect. RTL Architect allows designers to pinpoint inefficiencies in the HTL source code and in turn improve the HTL quality much earlier in the development schedule. It enables RTL designers to predict PPA and congestion impacts of their RTL changes earlier, significantly reducing the number of iterations you would need to close on the design goals later in your design cycle. RTL Architect includes a fast, high-capacity, multi-dimensional predictive engine, a unified data model for multi-billion gate capacity, and full chip hierarchical designs. It is built on Synopsys implementation and golden sign-off solutions, and includes an interactive, easy-to-use GUI that enables things like cross-probing for quick analysis and debug. Next, let me touch on 3D-IC Compiler. 3D-IC Compiler from Synopsys is the first unified platform for 3D-IC. It enables multi-die system integration, architectural exploration, design and analysis, and sign-off for your 3D-IC needs. And today, there are many point tool solutions that exist for 3D-IC, each with their own UI, scripting, use models, etc. But Synopsys 3D-IC Compiler is the first unified platform that allows you to consider the impacts of signal quality, power, thermal, and mechanical stress in a single environment. And finally, let me talk about the latest innovation from Synopsys that was recently announced, DSO AI, or Design Space Optimization AI. It is the first autonomous AI application for chip design that can explore trillions of combinations of inputs across the design space, making it possible to achieve PPA targets faster with fewer resources. Again, let me repeat that. Achieving PPA targets faster with fewer resources. And we all know resources are lacking today. DSO-AI leverages the full power of Fusion Design platform to enable significant improvements in productivity. It is very easy to deploy, and as one would expect it is cloud ready. DSO-AI allows designers to focus on innovation while automating the more menial, time-consuming tasks. So next, let me share with you a few results from customer designs that have leveraged DSO-AI to achieve the goals. So I'm showing you 4 results. You see 2 for ARM cores. One is an A78 and an A55, and a microcontroller and an AI engine. For every one of the designs, a single engineer deployed DSO-AI to quickly, in a week or so, get to the optimal PPA. And in most cases, DSO-AI was deployed on multiple projects simultaneously. The value of this technology is evident from the improvements that the engineers have seen. The first example, right? You can see improvements in Fmax, 4% improvement in Fmax, and now improvements in TNS at the same power levels, power footprint, I should say. For the A55 design, 5%, 6% improvement in Fmax, and a significant improvement in TNS with improvement in power. For the microcontroller, almost 30% improvement in power. And finally, for the AI engine, improvements in area, power, and TNS. So again, improvements across the board for all the designs. And it's important to note that these results were achieved in days by a single engineer instead of what would have taken weeks by a team of engineers. Again, let me repeat, achieving PPA targets faster with fewer resources. Okay, so in my brief today, I've talked about QUICs, the best starting point for ARM core CPU implementation, new groundbreaking technologies available with Fusion Design Platform, which include ML everywhere, or machine learning everywhere, that is deployed across the platform that delivers improved QR and TTR. RTL Architect, the first physically aware RTL analysis, optimization, and sign-off system. 3D-IC Compiler, the first unified platform for 3D-IC. And of course, DSO AI, the world's first autonomous application for chip design. So I'm now going to hand the presentation over to Holger, who's going to be covering innovation in design verification, focusing on virtual prototypes.
Thank you, Neel. So my name is Holger Keding, and I'm working in the verification group, or more precisely, in the virtual prototyping team. So as Neel already said, there are many examples of very close cooperation between ARM and Synopsys. And Neel just covered one topic, and I'll take you on a tour on using the virtual prototypes for early architecture exploration using ARM cycle models. So in the verification group, we are, of course, covering the classic verification topics from functional perspective, both block and SoC level verification, using different products and tools for simulation, checking, emulation, prototyping. But the verification continuum actually covers far more. So, for example, the aspect of using virtual prototypes for early software development using virtualizer, or this methodology you can use to develop software early in the design cycle and therefore kind of shift left your design cycle, reduce time to market, reduce costs, increase efficiency. So, and this flow is using ARM cycle models. And as the name suggests, they are fast, they are instruction accurate, they are functionally accurate, but timing is not modeled in great detail. So thus, they have the right abstraction and speed for this use case. But you can also use, or even use virtual platforms even earlier in the design cycle. So for early performance and power analysis, optimization and validation, also resulting in a shift left. For this use case, you use virtual platforms in Platform Architect that has dedicated tools, analysis, and models with higher timing accuracy. So, and ARM offers also processors and infrastructure models exactly for this use case. So these are the ARM cycle models that have the right level of abstraction exactly for this use case. ARM and Synopsys have been working very closely together to provide here an optimum solution and integration of these models into Platform Architect. And these early performance power analysis, optimization, and validation is the main focus of the presentation I have for you today. So let's take a look at the use cases for early architecture exploration using virtual prototypes. So what you see here on the left-hand side is one of these really very early explorations where most of your hardware is not fixed yet, so you don't know which processor maybe to take, or accelerators, what are the memory systems, interconnects you're going to need. So all of that is not fixed yet. And nor is the final software that will run on your system. So you might have some information on software that ran prior on the on a similar system, but not everything's fixed yet. So, and with Platform Architect Ultra, you can create workload models. That's what you see on the left-hand side. And these workload models are modeling the CPU load and the memory accesses of your final software. And these you can map to your workload, to your hardware model. And both workload model and hardware model are pretty abstract at this level. So you can easily make changes, swap out one processor for the next one, test what happens if you have more or less resources, and thus quickly, with short turnaround times, evaluate the different options. So much quicker, for example, than porting code from a CPU to a DSP, or even implementing this functionality in hardware. But of course, this is a very high level and predictive use case. So typically, The second or the next case would be, or the next step would be the validation and calibration case of this early analysis results. Now using the meanwhile at least partially available software, which you see here on the left-hand side, this application software, and more accurate hardware components. In this case here, you see ARM cycle models that are used here. So you have the M55 CPU, and you have a U55 Ethos micro NPU that runs, in this case, the inference of a CNN network. And that is integrated into a larger platform, so where you also have memory and interconnects, and this way kind of can build up your system. And with this system, you can validate also the prediction results you did earlier, and this way calibrate your higher level model, so that for your next project or for your next variant of this hardware, you have an even more accurate prediction. So these are two most important flows for architectural exploration using Platform Architect. And I talked now a lot about Platform Architect, so let's take a closer look what this tool is. So Platform Architect is a tool for creation and analysis of timing accurate virtual prototypes. So these virtual prototypes can be used from initial concept to architecture exploration, optimization, and validation. The key element of this entire methodology is also the extensive and very in-depth analysis capabilities that come with Platform Architect, and a large library of building blocks, so of models, processor models, of interconnects, of memory subsystems, of peripherals, so that you can easily stitch together your system and get started very quickly. So the models are available in different levels of abstraction. So you have starting from timing or from approximately timed to fully cycle accurate models. And in the latter category are also the ARM cycle models that play a major role in the overall architecture validation concept. So let's take a closer look at the value of these ARM cycle models in this overall flow. So ARM cycle models are first, of course, 100% cycle accurate models. So they indicate the true system performance. So they deliver reliable results. You can use accurate virtual prototypes to determine the best system architecture trade-offs and validate results for from your more abstract platforms. You can also easily use them for IP selection. So simply replace one model, replace it with another, rerun the simulation, and see what the performance delta is between these. So they are ideal for this use case of architecture design, IP selection, firmware development, and benchmarking. The accuracy even allows for optimizing critical code segments that are hardware dependent. So, and what we also provide, and that allows you to get started really quickly, is kind of starting systems that already come with a CPU, with an interconnect, and with memory, so that are pre-configured. So it allows you to get started in minutes rather than in days, and do quick turnarounds. And also, what is very important are the debug and performance analysis capabilities that come with these models that help you pinpoint the performance bottlenecks that might be in your system. So what you see here is a more detailed screenshot of this system that we've seen earlier. So in this case, we have an ARM Cortex M55 CPU and an Ethos U55 micro NPU. So just one example of the many ARM cores, other IP titles that are integrated into Platform Architect. And in this case, we are running the inference of a CNN layer. So the ARM cycle model for the CPU, the ARM, the Cortex M55 configures the micro NPU that you see on top here to do the heavy lifting parts of the inference layers. So of course, I mean, for this type of data hungry applications, the data access is also crucial. So even the fastest compute subsystem cannot perform if you cannot access the data at the same pace. And that's why also the right-hand part, so where these two cores are integrated, is very important. So the interconnect system and the memory subsystem that is or that shall be capable of providing the data at the right pace. And for this tailoring and optimization, you need, of course, good performance models for the interconnect and memory and other models as well. And that is all provided by Platform Architect out of the box. Different System C TLM models of interconnects, memories, processors. So let's go to the next slide, where we see that. Yeah, so this is a visualization of the result of such a simulation. So as a result of a Platform Architect simulation, you get an analysis database with performance measurements that you can trace or traces that you can slice and dice to help you analyze the performance bottlenecks, functional issues, or display the key performance indicators of your hardware. So what you see here, for example, on the very top, are transaction traces of the transactions that go over the bus on the very top from the ARM Cortex M55 system that kind of controls the entire system. Below that, you see the transaction traces of the ARM Ethos U55 that does the inference. And here you see that, so the first kind of burst is the reading the data, where it starts to process, then afterwards it's writing the data. On the graphs below, you see that during this inference, the throughput on the bus that you can measure increases, as well as the number of outstanding transactions. And below that, you see, for example, that also the DDR utilization. So these darker bars are the read excesses, so that go up while the inference or the U55 is reading data, and afterwards it's writing back the results. And you see that clearly. What you see on the very bottom is also that you can visualize the power and performance data back side by side. So you can do a combined performance and power analysis and optimization of such systems. So what you've seen on the last slide was the result of one single simulation. So the next step then typically is to refine the analysis by sweeping over different parameters of the hardware configuration. So this way you can gain insight on the impact of different parameters of your design, like outstanding transactions, the DDR memory speed, the frequency of the clock, or the size of the local memories. And with Platform Architect, you can easily configure such a simulation batch that is then all run in parallel. And Platform Architect extracts the performance data automatically, so that you can use that, for example, in Excel or Python for sensitivity analysis. And of course, if you still want to look at a single simulation, you can do root cause analysis, looking at graphs or traces, like you've also seen on the last slide. So, and with that, I'm already more or less at the end of my presentation part. Let me shortly summarize, and I hope you've seen the kind of the theme in this presentation. So ARM is advancing processor technology in scope and performance, and Synopsys and ARM are closely cooperating to provide the best solutions for our joint customers, both for early access to these processors, as Neel has described, to develop tools, flows, features to meet your project targets, and also using, for example, like I described, using ARM cycle models that are tightly integrated into Synopsys Platform Architect, and that can help shift left in the design flow and get to early and reliable architecture performance analysis and validation data. So, and as Neel also announced in the beginning, before we get to the end of this presentation, here comes a slide with the QR codes that you can scan to get more information on the technologies and topics that we've covered today. And with that, I'm really at the end of my presentation, and we both would like to thank you for your attention, and stay tuned.